Good morning, and thank you again, Barbara, to organize this very interesting workshop. So today I'm going to focus on lower mental dynamics, and I'm going to show you that it may be not so simple as far as rheology is concerned, and that that if we have a viscoplastic rheology in the lower mental, it may explain some large-scale features, such as fat plumes, slabs that are very expanded in the lower mental, and also maybe also the 1,000 kilometer depth horizons that we see in tomographic model. So we're going to use first observation, then the lab experiments, and we'll go back to the mental. So this work has been done with a lot of very talented undergrad, grad student, and postdoc, and also a lot of discussion with Patrick Cordier and Philippe Carrez in Lille. Okay, so we all know that if we look at the lower mental, first thing that we see, and it has been known for a long time, is that we have those two very large-scale structures, the LLSVPs, and those LLSVPs are delimited by the subduction, especially around the Pacific. They encase the surface hotspot, and there's probably chemical heterogeneities in those LLSVPs. So we can see it on individual tomographic models. We can also see it if we average a number of models first. Esmin was the first to do that, but since then there have been voting maps and so on, 2D, 3D, and the story is always the same. We have LLSVPs, two of them at least. We have structure in this LLSVPs, and there is chemical heterogeneities. So, so there's probably hot, but then the question is, are they denser or more buoyant? So if we look just at convection in a strongly temperature-dependent viscosity mantle, or in a sugar syrup, honey, mantle, then we see that it's very easy to have downwellings, cold downwellings that are encasing several plumes. You just need the convection intensity of the mantle, and you need also intermediate viscosity ratios. But if we look, and if you add some denser material here in the experiments, it's this bright color material at the bottom of your mantle, or here numerically in the real mantle, you still have the downwellings that are going to push around your LLSVPs, and so you're still going to end up with LLSVPs and upwelling surrounded by slabs. So the first order convection is I think is understood. Then if we focus now on those plumes, so they're responsible for the hotspot, and the beauty of it is that a number of the long-lived hotspots start with a big event, the traps, and then you have a thin volcano track. So if you look in a purely Newtonian, even strongly temperature-dependent viscosity fluid like honey, or a Newtonian mantle, you can have, your plume is going to be a big head followed by a thin conduit. So it would fit perfectly well those long track hotspots. But if you look at the scaling, at the physics of those plumes, you predict that the conduit diameter shouldn't be more than 100 to 200 kilometers. So this is really a big challenge for tomography, because we've heard a lot that it could not be resolved in the lower mantle. But as tomography improved, well, even in the early 2000s, there were large anomalies below hotspot that were imaged first by Tsao and also Knowledge Group in Princeton, and lately Barbara's model is doing exactly the same. And all those studies are showing that if your plume conduit is too small, so typically less than 600 to 400 kilometers in diameter, it's going to be, the signal is going to be very faint. So in short, you're not going to see thin plumes. And modeling is showing exactly the same. But however, if we look, for example, at the French and Romanowicz tomographic model, we're beginning to see very, very nicely bundles of upwellings that are showing up in the two LLSVPs. So here, the Pacific, and here, the Atlantic. So we have definitely fat plumes, because each of those plumes each of those upwellings in the bundles are 8 to 1,000 kilometers across at least. So how can we do that? So first of all, if the hot materials is less viscous, you're going to have a mushroom, so it doesn't work. Well, I mean, the conduit is too thin. So to get a fat plume just with a Newtonian fluid, you need a plume that is hot but more viscous. So one way of doing this is to increase a lot the grain size and to have a deformation by diffusion creep. But people could argue that it may be not really doable in a convective mantle. So another way of doing it is to have chemical heterogeneities. In fact, if in the bottom of your mantle you have some orange material that is intrinsically denser because of its composition, then to be able to rise, it will have to have a temperature anomaly that will be larger than the usual plume. And in fact, it's going to rise only if there's buoyancy ratio, which measure the density anomaly of compositional origin compared to the density anomaly of thermal origin. So this initial buoyancy ratio should be lower than 1. Otherwise, you're never going to be buoyant enough to counterbalance the denser material. In this case, if you have a buoyancy ratio that is between typically 0.4 and 0.8, you're going to have plumes that have a shape now that is much thicker than just the purely thermal one. And you can have plumes that are going to be really thermochemical at the bottom. And then you have an horizon where your red stuff is orange material is going to be cool enough now to be denser. So you're going to have an inner circulation into your thermochemical plumes. So this is because of this inner circulation that you're going to inflate the diameter of your upwelling. And we were talking earlier about anisotropy and how to see those kind of horizon. Well, that's if you have something that is doing this. So you're expecting that here you're going to have a maximum shear. And so that's where you should look for anisotropy and so on. Or reflection, off-phase reflection, like, for example, Tina Thomas' group is looking at in the Mantle. So you should expect those type of signature on top of those feature here. So if you consider thermochemical plume, yes, indeed, you can increase the diameter of your plumes. But if the buoyancy ratio is quite small, well, you still have quite thin plumes. So I know I've been one of the proponents of the thermochemical plumes, but I was not really completely satisfied because you're going to have, yes, fat plumes here, but here it's much more problematic. So is there anything else that we could think about? So, so we have fat plumes. Another thing that has been invoked several times since yesterday morning is that it seems to exist an horizon both for the upwellings going up and for the downwellings at about 800 to 1,000 kilometer depth. And this is not a known transition, phase transition. So a viscosity jump has been invoked, but it's still discussed what is the origin of this viscosity jump. You could have also chemical stratification. You could have beams. I mean, there have been a number of proposals to explain this horizon, but I think it's still very debated. And then the last thing is that if we look at the slab, well, in the upper mantle, they're much thinner than in the lower mantle. So they seem to have to increase their size to be able to go down. So what I'm going to propose is that what if those fat plumes, this horizon at the 1,000 kilometer depth, those fat slab, were due to the complex nature of lower mantle rheology? So, of course, the next question is why the lower mantle rheology should be more complex than just a Newtonian or weakly non-Newtonian behavior. Well, it's because we have several phases, Bridgmanite, ferropericlase, at least, and we have also texture. I mean, all those grains have a texture, especially if they have dislocation in them. And if you have also, at the larger scale, several phases intermingled, you're also going to have a texture. And if you have a texture, you can have jamming at first. So, in fact, in the everyday life, we know a number of materials that show jamming when the stress that you're applying on them is not big enough. So you have hair gel, you have toothpaste. The toothpaste, if you put it on your brush, well, it can sit there and it's not going to flow. If you apply shear strong enough, then it's going to nicely flow. So this behavior is really due to the small-scale texture of those fluids. So, for example, in air gel and toothpaste, you have carbopods. So it's those small polymer sponges, typically a 10 micron scale of microstructure. And so they're jammed together. And so because you have the friction, you have to apply a certain critical stress to have the material flow. So you can have also the same thing with grains, hydrogel grains, this time on the millimeter scale, and you still have a yield stress, a critical stress, above which you have motion, but under which you only have elastic deformation. So in engineering, this kind of material is represented by the in parallel combination of a purely elastic body, rigid body, and a nonlinear flowing liquid. So you're going to have, if sigma is a stress, you're going to have 4 stresses above a critical value, this yield stress here, sigma naught. You're going to have shear thinning. So this is really the purely viscous response to the motion. So we've been doing a lot of experiments with those fluings, so carbopol. So if you want to see a flow curve, so this is shear stress as a function of shear rate, you see that for very small shear rate, well, we are not going to 0, so there is really a critical shear stress, above which you can flow, and here we can have some shear thinning. So in this fluid, if I'm continuously, so I fill my tank or my mantle with this kind of fluid, and I'm heating from below, cooling from above, at a very well, nicely homogeneous temperature, well, I'm going to end up with a very unstable conductive temperature gradient. because in fact, because of the eustress, you need a finite amplitude perturbation to get motion to arise. So we did the experiment. At first, I didn't know that. So we put our fluid, and then 3 weeks later, we still had this conductive behavior, no motion at all. So I got really frustrated, and I just shake the box like this. And within 2 minutes, we have those beautiful instabilities. Because of course, if because of the shear, you've overcome the shear stress, then you just have a viscous fluids. And so you're going to have hot plumes and currents and all that. So we need to shake the tank. Well, the mantle cannot shake the tank. We saw very nicely yesterday that impact can shake the mantle tank. We don't have so much large impact right now, but I'm going to show you that localized heating is also a finite amplitude perturbation. So especially if you have compositional heterogeneities at the bottom of your mantle, you're going to have topography, and you're going to have differential heating. So for this type of mantle to work, well, it's good to have compositional heterogeneities. Otherwise, it would not work. I mean, a purely thermal mantle would really have trouble to convect. So here we have heating from a point source. This is 20 centimeter. And I'm sorry, the movie is not working, but I can show on my computer if anybody is interested. And the result is that instead of a mushroom, we're going to have a nice fat finger. So what is happening is that, okay, I'm building by purely thermal conduction a pocket of hot fluid, and this hot fluid is intrinsically buoyant. And so when the hot pocket is big enough, then the buoyancy force is going to be, the buoyancy of my hot pocket is going to be big enough to overcome the eustress, and then you have a plume that is going up. But this time, the structure of the plume is quite interesting. So here we have the velocity field. So those lines here are isotherms. So you have the thermal structure. And superimposed, we have the velocity field. So we see that there is strong shear, of course, at the bottom of your plume. And then in the middle, well, there isn't much activity, and most of the shear is really on the side of the plume. So we can look, so from the velocity, we can get the shear rate. So as I was telling you, maximum at the bottom, and then you have a local maximum again on the top of your plume. If we look at the viscosity structure, well, that's really interesting because, okay, we have lower viscosity around the plume at the edge of the thermal anomaly, but look at the viscosity inside. We have a plug flow. So here, it's like if the viscosity was nearly infinite. So yesterday, Thorsten mentioned this paper by Gurney's group showing that in the lower mantle, you would need a more viscous viscosity in the hot areas. Well, that's a way of doing it. I mean, for the motion, the viscosity is, of course, less viscous than the ambient mantle, but the core of the plume is much more viscous. So if you take an average, and I don't know what type of average you have to take to be relevant, and that has to be investigated, you could end up with a net signature of your plume that is more viscous, but it's not as simple as it is. And this type of velocity field geometry compared to the thermal anomaly is really very different from a purely thermal plume. Here, you see that, the shear is really extending a long way from both sides of the plume. And actually, so the shear is really very localized, and the motion is very localized. So here, it's a spatio-temporal, so this is height, and this is time, and on this upper figure here, it's on the edge here of the plume, and you see that the material, yes, is going up. The particles are going up. But what is very interesting is that very close to the plume, the particles are going down. And if I do the same here, they don't move. So you've localized all the shearing and the mass transfer around your instability, your upwelling. So, so in fact, to develop a plume, you have to have your density anomaly of thermal origin that is bigger and much bigger than the yield stress. So it gives you a first criteria. And, and so you're going to develop a fat fingers in a certain range of parameters here of this Y0 parameter. And, and in fact, we see that as soon as this criteria, so as your plume is going up, it's going to lose its temperature by thermal diffusion, in the surrounding mantle. And so you can reach a level where this criteria is not going to be true anymore. And then the plume can stop before reaching the surface. But actually, when we look more closely, we saw that there is a second criteria, in fact. And this time, it's on the balance between the yield stress and the viscous stress. And in fact, to get something that is continuing rising or continuing descending, you need to have those viscous stress that are bigger also than the yield stress. And if you balance those two, in fact, we see that we have onset when this Bingham number here is equal to 1. So it gives you the characteristic minimum strain rate in your system. And typically, we saw that the strain rate in the system, in the area that are moving, is between this value and about 10 times this value. And it depends only on the parameters of your rheology. So now, is there really a yield stress in the lower mantle? So when I discussing with colleagues about 10 years ago about this, and when I asked the question, well, I was asked very gently what I had been drinking or smoking. So, so I said, okay, maybe we're not going to publish that in earth science literature. But about 4 or 5 years ago, Patrick Cordier's group, looking at the behavior of dislocation in bridge monnet, so that in the lower mantle, deformation was probably mainly by dislocation climb. So in this case, each dislocation creates a stress field, and the network of dislocation creates a stress field. And then for dislocation to move, it can have to cross another dislocation. So you can see that, in fact, to start motion, you're going to have to overcome a critical stress that depends on the elastic property of your rock, but also on the density of dislocation. And in fact, this critical yield stress can reach a megapascal to about 100 megapascal for dislocation density between 10 to 8 and 10 to 12. And actually, so they showed that in the lower mantle, it was probably in this area that that the mantle rocks were behaving. So in fact, we can have in the mantle, in the lower mantle, if it's bridgemanite and it's deforming by dislocation climb, we can have a yield stress. So once the motion starts, it has been shown also that we have a shear thinning behavior. So you can derive all the parameters in your rheology. And this is going to depend strongly on the vacancy concentration into your crystal. And unfortunately, it's a parameter that is not very well known. So now we're going to use the fat plume framework to see if we can put some constraint in those, in the rheological parameters. So I'm going back to my Herschel-Berkeley rheological law in my viscoplastic, in my hair gel mantle. And so I can get the yield stress, the consistency, and the shear rate exponent. So if I plot again the flow curve, so the shear stress as a function of the strain rate. So this is when I have no critical shear rate. And you can see in this case that, yes, I have only the power law. And actually, the experiments are going to probe and measure only in this area here. Well, that's quite unfortunate because they will never be able to see a yield stress that can be inferred from climb creep in the mantle. Because we have yield stress typically of 1 to 10 or even 100 megapascal. And so in this case, you see that the part of the flow curve that is going to be influenced by it is for the low strain rate, but the mantle strain rate type of thing, 10 minus 15. So we can have, I think that we can safely say that we could have a yield stress in the mantle. The bad news is that we cannot measure it in the lab. But now if I apply my criteria, so I see that for a typical fat plume of about 800 kilometers, as seen in tomography, well, if this fat plumes at an average temperature of about 100 degrees or several hundred degrees Celsius, the yield stress, it's going to develop if the yield stress of the mantle is typically around 1 to 10 megapascal. So it's really consistent with the type of critical yield stress that is calculated by Lille's group. And then I've got also this other criteria on the viscous stresses being larger than the yield stress. And in fact, this is going to give me an information, a range of vacancy concentration that could see a plume that is rising from the bottom of the mantle, but then it would stop at the top of the mantle because of the pressure dependence of KV here. Then this criteria will not be satisfied anymore. So this could explain why we have an horizon at 1,000 kilometers. And then the last thing is that, okay, we've got hot plumes, but we can do exactly the same exercise for slabs. And then we see that for a 100-kilometer slab, if we have a yield stress of about 1 to 10 pascal second, well, it's not going to be able to intrude into this viscoplastic bridgemanite. However, if we got a pile, then it's going to penetrate. And so the answer to that is that we have to have a slab pile forming, so slab folding. So it had been shown in Newtonian fluid, and Thibaut Chassé did some really nice experiments in Carbopol. And we show indeed that, we have only piles that are coming down. And again, if you look at the shear rate, it's really concentrated around the descending pile here, and inside the conduit, once you have a conduit of pile coming down the CMB. So as a conclusion, I think that the plume morphology strongly depends on mantle rheology and composition. So it's really very important for geodynamics to have quantitative information about the morphology and also, of course, the temperature and compositional structure of the mantle, of a mantle upwelling, for example. So we need better tomographic image, as you all agree. Then the lower mantle might be viscoplastic. And because of dislocation climb, we could do the same exercise maybe with a mixture of two phases. I know that Marcel Tillman has done some very nice work about that. But we clearly need to investigate a lot more this possibility. So the bad news is that lab experiments will never see the shear stress. The good news is that if you have fat plumes because of viscoplastic rheology, you can also explain why there would be a 1,000-kilometer horizon in the mantle, and you can also explain why subductic piles can penetrate in the lower mantle, but not a single slab. So, thank you.